Tonight, picture the bright band of the Milky Way suddenly switching off. Every star you have ever seen with your own eyes, gone in an instant. You might expect nothing but empty blackness to remain, but you would be wrong. Because hovering above and below that vanished disk, something enormous would still be there. Ancient stars older than almost anything else in the galaxy. Streams of shredded companion galaxies. Clouds of gas wider than the disk itself. And a vast invisible cocoon reaching perhaps 10 times farther than the stars we can see. The glowing spiral, is only the thin, bright skin of something far larger and far stranger. Almost none of it shines in visible light. Almost all of it has been hiding in plain sight. Tonight, we find it. Before we go any further, if you find these deep dives into the cosmos worthwhile, a quick like or subscribe really helps this channel keep going. It only takes a second for you, but it makes a real difference for me. Now, let's begin. Let's start with the one word in tonight's question that trips almost everyone up. And it isn't a fancy astronomical term at all. It's the word above. When you say something is above you, you already know what you mean. You mean toward the ceiling, away from the floor, in the direction opposite to where a dropped stone would fall. Above is toward the sky, below is toward the ground. This works perfectly well because you live on the surface of a planet, and that planet has a very clear down. Gravity pulls everything toward Earth's center, and that single, unmistakable pull gives you a permanent, reliable sense of up and down that you never have to think about. But now, leave the surface of the Earth. Float out into space, far from any planet, and try to point up. You can't. There is no ceiling out there. There is no floor. A stone released beside you doesn't fall in any particular direction. Up and down, above and below, simply stop meaning anything because the thing that defined them, the pull of a planet beneath your feet, is gone. In the wider universe, there is no built-in up. There is no cosmic top and no cosmic bottom. The universe does not come with an arrow printed on it telling you which way is up. So when we ask what exists above and below the Milky Way, we are not talking about some absolute direction in space, because no such direction exists. We have to invent a reference, and the reference we choose is the galaxy's own shape. Here is the picture you need to hold in your mind. Our galaxy is not a shapeless swarm of stars, scattered evenly in every direction, like bees around a hive. It is a disk. A flattened, spinning platter of hundreds of billions of stars, all orbiting a common center, most of them confined to a relatively thin sheet. If you could pull far enough back and look at the Milky Way from the outside, from the right angle, it would look like a glowing pinwheel. A broad circular plate of light with graceful spiral arms winding outward and a swollen bright bulge at its heart. That flat sheet defines a surface, and astronomers call it the galactic plane. It's an imaginary flat surface slicing right through the thickest part of the disk, the way a knife might slice a pancake horizontally through its middle. And once you have that plane, above and below suddenly have meaning again. Above the galaxy means off to one side of that flat sheet, out of the plane. Below the galaxy means off to the other side. When we talk tonight about what lies above and below the Milky Way, this is precisely what we mean. Not up towards some universal ceiling, but perpendicular to the galaxy's own flattened disk, out into the space on either face of it. Now, this is where I have to be very careful, because there are two other flat surfaces that people constantly confuse with the galactic plane, and they are not the same thing at all. The first is the plane of our own solar system. The planets of our solar system also orbit in a roughly flat sheet, all of them circling the sun near the same level, like marbles rolling around the inside of a shallow bowl. That sheet is called the ecliptic. But here is the crucial point. The solar system's flat sheet is tilted with respect to the galaxy's flat sheet. They are not lined up. In fact, the plane of the planets is tipped at an angle of roughly 60 degrees to the plane of the galaxy. So the direction that is up out of the solar system is completely different from the direction that is up out of the Milky Way. When we say above the galaxy tonight, we are absolutely not talking about above the solar system. Those are two different tilts, two different flat sheets, pointing in two different directions. The second thing people confuse it with is the celestial equator, which is simply Earth's own equator projected outward onto the sky, the line the sky seems to turn around as our planet spins. That too is tilted at its own strange angle relative to the galaxy. So we now have three flat sheets, all tipped at different angles. Earth's equator projected on the sky, the solar system's plane of planets, and the galaxy's plane of stars. Tonight we care about only the last one, the galactic plane. Everything we explore hangs above or below that particular sheet, and no other. Good. With that settled, let's actually go there. Let's rise up out of the galactic plane and watch what happens to the galaxy around us. Start right where we live, deep inside the disk, embedded among the ordinary stars. Down here, in the thin sheet where the sun resides, the galaxy is a busy, crowded, dusty place, at least by cosmic standards. There is gas, there is dust, there are young stars and old stars, star-forming clouds, glowing nebulae, and the spiral arms sweeping past. This thin central layer is where nearly all the action happens, where new stars are still being born today. It is called, appropriately, the thin disk, and it truly is thin. The Milky Way spans something like 100,000 light years from edge to edge, but this bright thin disk is only around 1,000 light years thick. Think about that ratio for a moment. 100,000 across, 1,000 thick. That means the disk is around 100 times wider than it is thick. To make that real, imagine shrinking the galaxy down to the size of a large dinner plate, say a foot across. At that scale, the bright thin disk of stars would be thinner than a sheet of cardboard laid on the plate. The galaxy is proportionally flatter than a pancake, flatter than a compact disk, flatter than almost any everyday object you could name. It is a spectacularly flat structure, and this flatness is exactly why the plane matters, and why above and below are such meaningful directions. There is a great deal of galaxy spread out sideways, and comparatively very little of it stacked vertically. So the moment you start climbing out of the plane, you leave the crowd behind very quickly. Let's climb then. Rise straight up, out of the thin disk, away from the sun, perpendicular to the plane. What happens? The first thing you notice is that things thin out, fast. The stars, the gas, the dust, all of it grows sparser with every light year you ascend. Down in the plane, stars are relatively close together. Rise a few hundred light years, and there are noticeably fewer around you. Rise 1,000, and fewer still. The density of material doesn't drop off gently and evenly either. It falls away steeply, dropping by roughly half every few hundred light years at first. The galaxy fades beneath you like a city's lights, fading as an airplane climbs after takeoff. The bright, dense grid below dissolving into scattered, lonely points. But And this is one of the most important ideas in tonight's whole story. The density never actually reaches zero. It gets smaller and smaller, thinner and thinner, but it never becomes truly, perfectly empty. There is no clean line, no sharp wall, no altitude at which you suddenly pop out of the galaxy into pure nothingness. Instead, the galaxy simply trails off, growing ever fainter, ever more diffuse, fading gradually into the dark. This matters enormously, because it means the space above and below the disk is not empty. It is sparse, and sparse is a very different thing from empty. A desert is sparse. It is not empty. There is life out there in the thin heights above the galaxy, just spread very, very thin. And as you climb, something else changes. Not just how much is around you, but what kind of thing is around you. Because it turns out the galaxy is not a single flat layer at all. It is built from layers stacked on top of one another, like the strata in a canyon wall, and each layer is made of a different sort of star. The first and thinnest layer is the one we've already met, the thin disk, where the sun lives, full of gas and dust and fresh young stars. But as you rise out of it, you pass into a second, puffier layer that surrounds and envelops the thin disk. Astronomers call it the thick disk. The thick disk is spread over a greater height, several times taller than the thin disk, reaching perhaps a few thousand light years above and below the plane. Its stars are more spread out, and crucially, they are different. They are, on the whole, considerably older than the stars of the thin disk, and they move differently, following orbits that carry them up and down through the plane, rather than staying neatly within it. Rise higher still, beyond even the thick disk, and you enter the third and by far the largest layer, though also the emptiest. This is the stellar halo, and the stellar halo is a genuinely astonishing thing. Unlike the disks, which are flattened sheets, the stellar halo is roughly spherical, a vast, faint, rounded cloud of stars enveloping the entire disk in every direction, above, below, and all around, like the fluffy sphere of a dandelion head surrounding its stem. It reaches enormously far, extending tens of thousands of light years out from the center, far above and below the bright plane. Its stars are spread so thinly that if you lived on a planet out in the halo, your night sky would be nearly black, sprinkled with only a scattering of faint, distant stars. And off in one direction, you would see the bright disk of the galaxy edge on, a glowing river of light hanging in the darkness. The halo holds only a tiny fraction of the galaxy's stars, a few percent at most, but it occupies a titanic volume. It is the sparse, ancient, outermost shell of the stellar galaxy. So we have three layers, stacked and nested. The thin disk within the thick disk, within the great spherical stellar halo. And here is the beautiful part. As you climb through them, you're not just moving through space, you are moving through time. Because the higher you go, the older the stars around you tend to be. Why should that be? Why should the stars stacked above and below the plane be so much older than the ones down in it? To understand this, we need to talk about what stars are made of, and how that has changed over the enormous history of the galaxy. When the universe was young, shortly after its beginning, it contained essentially only the two lightest elements, hydrogen and helium. That was almost the entire menu. There was no carbon, no oxygen, no iron, no silicon, none of the heavier elements that make up rocky planets and living things. Those heavier elements did not yet exist because they are forged inside stars. A star spends its life fusing light elements into heavier ones in its core, And when massive stars die in titanic explosions, they scatter those freshly minted heavy elements out into space. That enriched gas then gathers into new stars, which are born already seasoned with a pinch of heavy elements inherited from the generations that died before them. Those stars live and die and enrich the gas further still, and so, over billions of years, the galaxy's gas has grown steadily richer in heavy elements with each passing generation of stars. Astronomers have a slightly odd word for all the elements heavier than hydrogen and helium. They call them, collectively, metals. Even elements like oxygen and carbon that a chemist would never call a metal. It's just astronomical shorthand for everything beyond the two lightest elements. And they describe a star's chemistry by how much of these so-called metals it contains. A star rich in heavy elements is called metal-rich. A star with very few of them is called metal-poor. Now the logic clicks into place. The older stars in the galaxy, the ones that formed in the earliest days when the gas had barely been enriched at all, are metal-poor. They were built from nearly pure hydrogen and helium, because that was almost all there was. The youngest stars, forming today from gas that has been enriched over billions of years by countless earlier generations, are metal-rich. So a star's metal content is like a birth certificate. It roughly tells you when that star was born. Metal-poor means ancient, metal-rich means young, and when astronomers measure the stars in each of the galaxy's layers, they find a striking pattern. The thin disk, down in the plane, is full of relatively metal-rich stars, young stars, and middle-aged ones, like the Sun, born from well-enriched gas. But the thick disk stars are, on average, older and more metal-poor, and the stars of the great spherical halo, high above and below the plane, are the most extreme of all, extraordinarily old and dramatically metal-poor. Some halo stars are among the oldest objects known anywhere, having formed over 12 billion years ago, in the galaxy's distant infancy. When you look at a star way up in the halo, you're very often looking at a genuine relic, a stellar fossil that has been quietly orbiting through the darkness above the disk since long before the Sun, the Earth, or the thin disk itself even existed. This is a profound realization. The space above and below the galaxy is not just physically distant from the bright disk. It is, in a real sense, a window into the deep past. The disk is the galaxy's bustling, ever-renewing present. The halo, hanging far above and below, is its ancient frozen history, preserved in the chemistry of stars that stopped being made a very long time ago. But there's more to these high-flying stars than just their age and chemistry. There's the matter of how they move, and their motion tells a story every bit as revealing. The stars of the thin disk, like the Sun, move in a very orderly, disciplined way. They travel in nearly circular orbits, all going around the galactic center in the same direction, all staying close to the plane like cars on a vast circular racetrack, all in their lanes, all going the same way. It's a smooth, flat, rotating pattern, and it's why the disk is a disk in the first place. Orderly circular motion in a shared plane naturally produces a flattened, spinning platter. But the stars of the halo don't do this at all. Their orbits are wild by comparison. Instead of neat circles staying near the plane, halo stars follow long, plunging, elongated orbits, diving in towards the galactic center and then swinging far back out again, tilted at every conceivable angle. Some orbit one way, some the other. Some plunge nearly straight through the center. Their paths carry them high above the plane and then far below it, again and again, like comets on enormous looping trajectories rather than cars on a racetrack. This is exactly why the halo is round rather than flat. A swarm of stars all following steeply tilted, plunging orbits at every angle naturally fills out a rough sphere, not a disk. The shape of the halo is written directly in the motions of its stars, and this difference in motion is not a coincidence. It's another clue about origins. One will follow much further later on. Orderly, flat, circular motion is what you get when material settles gently into a rotating disk over time. Wild, plunging, randomly tilted motion is what you get from a more violent, chaotic history. Stars that were flung onto those paths long ago and have never settled down. The calm disk and the chaotic halo are telling us they came to be in very different ways. So already, just by rising up out of the plane, we've discovered something remarkable. The galaxy is layered. It has a thin, young, orderly, metal-rich disk of stars, wrapped in a thicker, older disk, all of it embedded inside a vast, ancient metal core, chaotically orbiting spherical halo of stars that extends far above and below the bright plane we see. The Milky Way we recognize, that bright band across the sky, is really just the innermost, flattest, most crowded slice of a much taller, rounder structure. And yet, even the stellar halo, sparse and ancient as it is not the last of the stars above and below the plane. Because scattered through the halo, orbiting far outside the bright disk, high above and far below the plane, are some of the most spectacular and revealing objects in the entire galaxy. To see them, and to understand why they matter so much, we need to talk about globular clusters. Imagine taking hundreds of thousands of stars, sometimes even 1 million, and packing them together into a single, roughly spherical swarm, just a few dozen to perhaps a couple hundred light years across. Down in our neighborhood in the thin disk, stars are separated by several light years each. The sun's nearest neighbor is over 4 light years away. But in the crowded heart of one of these swarms, stars can be packed hundreds or even thousands of times more densely. If you lived on a planet deep inside one, your night sky would blaze with thousands upon thousands of stars, many of them shining as brightly as the brightest planets look from Earth. Some bright enough to cast shadows, the whole sky glittering so densely that true darkness would never fall. These dazzling, densely packed stellar cities are called globular clusters, from the word globe, because they are so beautifully spherical. The Milky Way possesses somewhere around 150 of them that we know of, and possibly more still hidden behind the dust of the disk. And here is the key fact for our story tonight. Globular clusters do not, for the most part, live down in the thin disk with the sun. They orbit the galaxy out in the halo, on those same steeply tilted, deeply elongated paths, swinging high above and far below the galactic plane. They are, in a sense, satellites of the whole galaxy, each one a compact swarm of hundreds of thousands of stars looping through the vast, sparse space that surrounds the disk. And like the halo stars they travel among, globular clusters are ancient. Almost every one of them is enormously old, typically well over 10 billion years, and correspondingly metal poor. They are among the oldest structures in the entire galaxy, tight-knit families of stars that were born together in the galaxy's earliest days and have stayed bound together by their mutual gravity ever since, orbiting patiently through the heights above and below the plane for the whole long history of the Milky Way. When you look at a globular cluster, you're looking at a coherent piece of the young galaxy, preserved almost intact across more than 10 billion years. Now here is why these clusters matter far beyond their own beauty, and it's one of the great stories in the history of astronomy. Because globular clusters are bright, containing so many stars concentrated in one place, and because they range far out of the dusty plane where they can be seen clearly, they can be spotted at enormous distances all across the sky. And roughly a century ago, an astronomer named Harlow Shapley realized that this made them extraordinarily useful. He reasoned that if these clusters were true satellites of the whole galaxy, then their distribution across the sky should trace out the real shape and center of the galaxy, rather than just the local neighborhood of stars around us. So he mapped them. He measured the directions and distances to the globular clusters he could find, and he plotted where they sat in 3 dimensions. And what he found overturned everything. Before Shapley, most astronomers assumed the sun sat at or near the center of the galaxy. It was a natural enough assumption. When you look out at the disk of stars around us, it seems to stretch roughly equally in all directions along the plane, which makes it look as though we're in the middle. But the globular clusters told a completely different story. They were not spread evenly around us. They were lopsided, overwhelmingly concentrated toward one particular region of the sky, in the direction of the constellation Sagittarius. The whole swarm of clusters was centered not on us, but on a point tens of thousands of light years away in that direction. Shapley drew the only sensible conclusion. That distant point, around which all the clusters swarmed, must be the true center of the galaxy. And the sun, far from sitting at the center, was way out in the galaxy's suburbs, tens of thousands of light years from the middle. It was a Copernican shock all over again. Just as Copernicus had removed the Earth from the center of the solar system, Shapley now removed the sun from the center of the galaxy, using nothing but the pattern of these ancient star clusters hanging above and below and around the disk. The very fact that globular clusters live out in the halo, ranging clear of the dusty plane, is what allowed them to reveal the galaxy's genuine architecture. They stood high enough above the crowd to show us the true shape of the thing we were standing inside. And that, right there, is the heart of tonight's whole revelation, previewed in a single historical discovery. The bright, flat disk of stars we see is not the galaxy. It is a slice of the galaxy. The real structure is bigger, rounder, older, and far more three-dimensional than the glowing band across the sky suggests. And much of its true nature is only revealed by looking at what lies above and below the plane, not within it. Shapley found the galaxy's center and our own humble place within it, not by studying the bright disk, but by studying the faint, ancient, high-flying clusters that orbit outside it. So let's take stock of where we've climbed to. We began by realizing that above and below are not universal directions at all, but are defined entirely by the galaxy's own flattened plane, a plane tilted differently from the solar system's plane and from Earth's equator projected on the sky. We found that this plane holds an astonishingly flat, thin disk, proportionally flatter than a pancake, where the sun and the young, metal-rich stars live. We rose up out of it and watched the density of stars, gas and dust, fall away steeply, though never quite reaching zero, so that the space above and below is sparse but never truly empty. We passed through the puffier, older thick disk, and then into the vast, roughly spherical stellar halo, where ancient, metal-poor stars follow wild, plunging orbits at every angle, preserving the chemistry and motion of the galaxy's distant youth. And we met the globular clusters, dazzling ancient swarms of hundreds of thousands of stars orbiting far out in that halo, high above and far below the plane, whose distribution first revealed to us the true center and shape of the galaxy we live in. But notice what all of this has been so far. It has all been about stars. Old stars, young stars, clustered stars, scattered stars, and that leaves an enormous question hanging in the darkness above and below the disk. Because the galaxy is not made of stars alone. Stars, for all their brilliance, are only the parts that shine. Woven between them and stretching far beyond them is gas. Vast quantities of it, in clouds and streams and rivers that reach up out of the plane and arc across the sky in ways that stars never do. And some of that gas doesn't even belong to the Milky Way in the first place. Some of it is being torn from other galaxies entirely. Galaxies that orbit our own from far above and below, and dragged out into long, luminous ribbons draped across the heavens. That is where we go next. We leave the realm of the stars behind and enter the realm of the gas, and of the smaller galaxies that circle ours from high above and far below the plane, shedding their material into the darkness as they go. We've been treating the space above and below the galaxy as a place of stars, sparse and ancient though they are. But now I want you to imagine turning off the starlight entirely, and switching on a different kind of vision, one that lets you see cold hydrogen gas instead. Because if you could do that, the sky above and below the Milky Way would suddenly light up in a way that would astonish you. You would see it draped in enormous glowing ribbons and streamers, vast arcs of gas stretching across huge swathes of the heavens, far longer and far stranger than anything the stars alone reveal. And the story of where that gas comes from and where it's going is one of the most dramatic in the whole galaxy. To begin it, we have to meet the Milky Way's companions, because our galaxy, for all its grandeur, does not sail through space alone. It is orbited by a whole retinue of smaller galaxies, dozens of them, circling the great disk like moons circling a planet, and many of them ride on paths that carry them high above and far below the galactic plane. The two most famous of these companions are visible to the naked eye, though only from the southern half of the world. If you stand under a dark sky somewhere in the southern hemisphere and look up, you'll see two soft, luminous smudges, like detached pieces of the Milky Way that have drifted away from the main band. For thousands of years, the peoples of the southern continents knew these smudges intimately and wove them into their stories and navigation. To European sailors, they became known centuries ago as the Magellanic Clouds, after the expedition that first carried word of them back across the world. And for a long time, nobody knew what they truly were. They looked like clouds, faint and fuzzy. But they are not clouds of gas hanging in our own sky. They are entire galaxies, separate collections of billions of stars, orbiting our Milky Way from tens of thousands of light years away. There are two of them, and they are not the same size. The large Magellanic Cloud is the bigger of the pair, a chaotic, irregular galaxy holding perhaps 10 to 20 billion stars, along with rich stores of gas and vigorous regions of new star formation. If the Milky Way is a great city, the large Magellanic Cloud is a sizable town in its own right. The small Magellanic Cloud is fainter and less massive, a more ragged scattering of a few billion stars. Both are dwarfed by the Milky Way, which outweighs them many, many times over. but both are substantial, real galaxies, and both are close enough, in cosmic terms, that we can study their individual stars in exquisite detail. They are the two grandest members of the Milky Way's family of satellite galaxies. But they are far from the only members. Over the past decades, astronomers have discovered dozens more satellite galaxies orbiting the Milky Way, and most of them are nothing like the bright Magellanic clouds. They are dwarf galaxies of the faintest, most tenuous kind, and some of them are almost unbelievably feeble. There is a whole class known as dwarf spheroidal galaxies, small rounded swarms of stars that contain, in some cases, only a few million stars, or even just a few thousand. These are so faint, so diffuse that they were only found by carefully sifting through star catalogues and noticing a subtle overdensity of stars in one small patch of sky, a barely perceptible thickening of the darkness. Some of the faintest known galaxies in the entire universe are these ultra-faint dwarfs orbiting our own Milky Way, so dim that they contain fewer stars than a single bright globular cluster, yet spread across a far larger region of space. It's worth pausing on a few of these companions individually because they are not interchangeable smudges. Each has its own character and its own path through the heights, above and below the plane. There is the Sagittarius dwarf, a galaxy that has strayed so close to the Milky Way that it is being actively torn to pieces right now. Its stars streaming away from it as it plunges nearly over the poles of our disk, above the plane on one side of its orbit, and far below it on the other. There is Fornax, a rounded dwarf that carries a small retinue of his own star clusters, orbiting far out in the halo. There is Draco, one of the faintest and most heavily dark matter-dominated galaxies known, a feeble puff of a few 100,000 stars that would hardly hold together at all without an enormous invisible mass gripping it. There is Sculptor, and a dozen more, each on its own tilted, elongated orbit, some swinging out to enormous distances and taking billions of years to complete a single lap. And here is a genuinely startling pattern that has emerged from mapping where these satellites sit and how they move. They do not appear to be scattered randomly around the Milky Way in every direction, as you might naively expect. A great many of them seem to lie, roughly, within a single vast flattened sheet, a broad plane of satellites that is tilted steeply, almost at right angles, to the plane of the galaxy's own disk. Picture the flat platter of the Milky Way, and then picture a second enormous flat arrangement of dwarf galaxies standing nearly on its edge, slicing through the heights above and below the disk like a great wheel set perpendicular to a plate. Astronomers are still debating exactly how real and how tight this arrangement is, and why it should exist at all. Because our best models of how galaxies gather their satellites predict a much messier, more spherical scattering. But the observation that so many of the Milky Way's companions ride within a single steeply tilted structure, threading the space directly above and below the plane, is one of the intriguing puzzles of galactic astronomy today. Whatever its ultimate explanation, it means the family of satellites is not a random halo of hangers-on, but something with a shape, a preferred orientation, carving through the vertical space on either side of the disk. And this is the point that matters most for tonight. Because those tilted orbits and that steeply inclined sheet mean the satellites spend much of their time well off the plane, at this very moment, many of them hang in the space directly above or below the bright band of stars. The Magellanic clouds among them, riding their own path tipped sharply out of the galactic plane. So when you ask what lies above and below the Milky Way, part of the honest answer is simply this: whole other galaxies. Smaller ones, yes, and fainter ones, but genuine galaxies, complete with their own stars and, in many cases, their own gas, wheeling through the heights and depths on either side of the disk, close enough to be studied star by star, and yet unmistakably separate worlds. And it's the gas that leads us to the next great revelation. Because the Magellanic Clouds are not simply passing by untouched. They are locked in a slow, violent, gravitational relationship with the Milky Way, and with each other. And that relationship is tearing them apart. Think about what happens when a smaller object passes close to a much larger one. The larger body's gravity pulls harder on the near side of the smaller object than on its far side, because gravity weakens with distance. This difference in pull, stretching the near side away from the far side, is called a tidal force. It's the same basic effect by which the moon raises tides in Earth's oceans. But when a whole galaxy passes near a much more massive galaxy, the tidal forces don't just raise gentle tides, they can rip material clean off the smaller galaxy and fling it out into space in long streamers. One drawn out ahead of the galaxy, and one trailing behind, like ribbons torn from a flag caught in a gale. That is exactly what has been happening to the Magellanic Clouds. Over hundreds of millions of years, as they have orbited the Milky Way and swung around one another, the combined tidal forces have pulled great quantities of gas out of them, stretching that gas into an enormous ribbon that now arcs across the sky. And when I say enormous, I mean it. This ribbon of stripped gas, known as the Magellanic Stream, stretches across a truly vast fraction of the entire sky, wrapping more than 100 degrees around us, more than 140 degrees by many measurements, which is well over a third of the way around the whole celestial sphere. It is one of the largest coherent structures anywhere near our galaxy, a river of hydrogen torn from our companions and draped across the heavens, high above and below the plane. You cannot see the Magellanic Stream with your eyes or with an ordinary telescope, because it does not shine in visible light. It is cold hydrogen gas, and cold hydrogen betrays itself in a very particular way that transformed our understanding of the galaxy. Neutral hydrogen atoms emit a faint radio signal at a very specific wavelength, close to 21 centimeters. It's a whisper, but it is a whisper at a precise, unmistakable pitch, and radio telescopes tuned to that wavelength can map cold hydrogen gas across the sky, even where there is not a single visible star to be seen. When astronomers turned such telescopes on the region around the Magellanic Clouds, the stream appeared, an immense arc of hydrogen glowing softly in the radio, tracing the path of the devastation the Milky Way's gravity has wrought upon its companions. And the stream is not the only piece of this wreckage. Astronomers have identified several related structures. There is a bridge of gas running directly between the large and small Magellanic Clouds, called the Magellanic Bridge, marking where the two galaxies have pulled material out of each other in their own mutual dance. And there is a feature called the leading arm, a stream of gas running ahead of the clouds along their orbit, torn off and flung forward rather than trailing behind. Together, the stream, the bridge, and the leading arm form a whole complex of stripped gas, a sprawling monument to the ongoing dismemberment of the Magellanic Clouds, spread across an immense region above and below the galactic plane. The leading arm deserves a closer look, because it poses a puzzle that the trailing stream does not. And the contrast between the two is revealing. When tidal forces strip gas from a moving galaxy, the most natural thing to expect is a trailing tail, material pulled off and left behind along the orbit, lagging as the galaxy races ahead, exactly like the wake behind a boat. The Great Magellanic Stream is essentially this trailing wake, gas falling behind the clouds as they travel. But the leading arm runs the other way. It is gas that sits ahead of the Magellanic clouds along their path, flung forward rather than dragged behind, and forward-flung debris is much harder to produce by simple stripping. It's as though the boat's wake somehow appeared in front of the bow. Producing a leading tail requires a more intricate gravitational choreography, in which some of the stripped gas is pulled onto a slightly tighter, faster orbit than the clouds themselves, and so races ahead of them, or is gravitationally slung forward during a close encounter. The details are still argued over, and the leading arm has become a testing ground for competing models of exactly how the clouds have moved and interacted over the past few billion years. Some of that gas may also be interacting with the tenuous outer gas of the Milky Way itself, being slowed and shredded as it plows through it, which would leave its own signatures in the shape and clumpiness of the arm. The point, for tonight, is that the wreckage strewn above and below the plane is not a single simple tail. It is a complex, two-sided structure, trailing behind and reaching ahead, each side encoding a different piece of the gravitational story, and astronomers read that shape the way you might read the spray pattern of a collision to reconstruct what happened and in what order. What will become of all this gas? This is where the story turns from destruction to something almost like renewal, because the gas of the Magellanic Stream is, in a sense, on a long, slow journey toward the Milky Way. Much of it is destined, over hundreds of millions of years, to be drawn inward and eventually to rain down onto the disk of our galaxy. And when it arrives, it will be fresh fuel, raw hydrogen that can cool, gather into clouds, and one day collapse into new stars. The Milky Way has been steadily forming stars for billions of years, and one of the long-standing puzzles is how it keeps finding enough gas to do so. Left to itself, the disk should have run low on star-forming material long ago. The stripping of satellite galaxies and the slow infall of streams like the Magellanic Stream may be part of the answer. In tearing its companions apart, the Milky Way is also, over vast spans of time, feeding itself. The gas torn from the clouds above and below the plane is future starlight, still on its way in. This idea, that gas is not just sitting statically above and below the galaxy, but is actively falling toward it, brings us to one of the most intriguing and genuinely unresolved features of the space around the Milky Way. Because the Magellanic Stream is not the only gas up there behaving strangely. Scattered all across the sky, above and below the plane, radio telescopes have found clouds of hydrogen that are moving in ways that make no sense if they simply belong to the calmly rotating disk. These are called high-velocity clouds, and they are one of the great open questions of galactic astronomy. Here is what makes them puzzling. The gas of the disk rotates with the galaxy in an orderly, predictable way. So if you measure the motion of gas in a given direction, you can predict roughly how fast it should appear to be moving, given the galaxy's rotation. But the high-velocity clouds break these rules. They move at speeds and often in directions that don't match the expected rotation at all. Some of them appear to be falling inward, toward the galactic plane, from high above or far below. They are clouds of hydrogen, sometimes quite large, hanging in the halo above and below the disk and plunging toward it at high speed. And the pressing question, one that astronomers have debated for decades and still argue about today, is a simple one to ask and a hard one to answer. Where do they come from? There are several leading possibilities, and the honest position is that different high-velocity clouds may have different answers. It is not one single phenomenon with one single origin, but likely a mixture. One possibility is that some of this gas is arriving from outside the galaxy altogether. The Milky Way sits within a larger cosmic environment, threaded with tenuous gas, and over cosmic time, fresh gas from the wider universe can drift inward and fall onto the galaxy. Under this picture, at least some high-velocity clouds are pristine or near-pristine hydrogen, gas that has never been part of the Milky Way before, being captured for the first time. This would be another form of the galaxy feeding itself, drinking in raw material from its surroundings to fuel future generations of stars. Some high-velocity clouds do appear to be relatively poor in heavy elements, which is consistent with this idea, since gas that has never been processed inside stars should carry few of those elements. A second possibility is that some of these clouds are debris from the ongoing destruction of satellite galaxies. Gas torn off dwarf companions or associated with structures like the Magellanic stream, caught in the act of falling in. In that case, the high-velocity clouds are pieces of the same story we've just told. Fragments of shredded companions descending toward the disk. And a third possibility, distinct from both, is that some of this gas didn't come from outside at all, but was thrown up out of the disk by the galaxy itself and is now falling back down. This third idea is so important and so beautiful that it deserves to be told in full, because it reveals the space above and below the plane as something almost alive, breathing gas out and drawing it back in a slow, majestic cycle. To understand it, we have to go back down into the disk, to the places where stars are born and where they die. In the crowded star-forming regions of the thin disk, the most massive stars live short, furious lives. A star many times the mass of the sun burns through its fuel in just a few million years, and then dies in a catastrophic explosion, a supernova, briefly outshining billions of ordinary stars and blasting its outer layers outward at enormous speed. And these massive stars are not born alone. They form in clusters, dozens or hundreds of them together. So their deaths often come in clusters too. A whole neighborhood of massive stars exploding within a relatively short span of cosmic time. When many supernovae detonate close together, along with the fierce winds that pour off massive stars even before they explode, their combined energy does something remarkable to the surrounding gas. It heats it to enormous temperatures and blasts it outward, carving out great bubbles of hot gas within the disk. And if the eruption is powerful enough, these bubbles can punch right through the thin layer of the disk and burst out of the plane entirely, venting hot gas upward, out into the space above and below like a geyser erupting from the surface of the Earth. The gas, superheated and flung upward by the collective violence of dying stars, rises high out of the disk, thousands of light years up into the halo. But it cannot rise forever. The galaxy's gravity still has hold of it. So the hot gas climbs, slows, and begins to cool as it goes. And as it cools, high above the plane, it condenses, gathering back into clouds, growing denser and heavier. Eventually gravity wins, and the cooled gas begins to fall back down toward the disk from which it was launched, raining back onto the galaxy thousands of light years from where it first erupted. Gas goes up, hot and fast, driven out by exploding stars. Gas comes back down, cooled and condensed, pulled home by gravity, up and out, then cool and back. It is a cycle, a continuous circulation of matter between the disk and the space above and below it. Astronomers have given this magnificent process a wonderfully evocative name. They call it the galactic fountain. And the image is exactly right. Just as a water fountain shoots liquid upward, only for it to arc over and fall back into the basin to be pumped up again, the galactic fountain shoots gas out of the disk, lets it rise and cool, and then draws it back down to be recycled into the next generation of stars. And under this picture, at least some of the high-velocity clouds we see falling toward the disk are the descending arm of this fountain. Gas on its way back down after having been hurled aloft by supernovae ages ago. Think about what this means for the space above and below the plane. It is not a still, dead, empty region that the galaxy merely happens to sit within. It is an active part of the galaxy's metabolism. The disk exhales gas into it through the fountain. The halo lets that gas cool and rain back down. Fresh gas drifts in from the Magellanic stream and from the wider universe. Satellite galaxies are torn apart and add their material to the mix. The heights above and below the Milky Way are a churning, dynamic arena where gas is constantly rising, cooling, falling, and being recycled, feeding the ongoing birth of stars far below. Far from being empty, this region is where much of the galaxy's future is quietly being prepared. And it's worth pausing on just how varied the gas up there turns out to be, because it reflects these different origins. Some of it is hot, having been recently heated by supernovae or shocks. Some is cool, having had time to condense. Some is relatively rich in heavy elements, betraying that it was processed inside stars in the disk before being flung upward, exactly what you'd expect for fountain gas. And some is notably poor in heavy elements, hinting that it is fresh material arriving from outside, never before touched by a star. By measuring the chemistry, the temperature, and the motion of these clouds, astronomers can begin to sort out which ones are the descending arm of the fountain, which are shredded pieces of companions, and which are pristine gas falling in from the cosmos beyond. It is painstaking work, and it is not finished. There are individual clouds whose origins remain genuinely disputed. But the broad picture of gas cycling and gas arriving, of the halo as a place of constant traffic, is now firmly established. Let me give you one particularly striking example to make all of this concrete, because it's easy for these vast, diffuse structures to feel abstract. There is a specific, well-studied, high-velocity cloud, an enormous one that has been tracked in detail as it plunges toward the galactic disk. It is a titanic mass of hydrogen, containing enough gas to build a great many stars, and it is on a collision course with the disk of the Milky Way, expected to slam into the plane in tens of millions of years. When it does, it will compress the gas already there and very likely trigger a burst of new star formation, lighting up that region of the disk with freshly born stars. Here, then, is a single object we can point to, high above the plane and falling fast, that carries within it the raw material for a future generation of stars, and that will, in the astronomically near future, deliver that material to the disk in a dramatic impact. It is the galactic fountain, or the infall of fresh gas, caught in the act, a piece of the galaxy's future descending toward us out of the dark. So now, Stack this new layer of understanding on top of what we found before. Earlier, we rose out of the plane and discovered layers of stars. The thin disk, the thick disk, and the great spherical stellar halo of ancient metal-poor stars on their long looping orbits, dotted with the dazzling globular clusters that first revealed the galaxy's true shape. Now we've discovered that woven through and beyond those stars is a whole second galaxy made of gas, invisible to the eye, glowing softly in the radio. The vast arc of the Magellanic stream torn from our companions, the swarm of tilted satellite galaxies riding high above and far below the plane, the enigmatic high-velocity clouds falling inward from every direction, and the ceaseless breathing of the galactic fountain lifting gas out of the disk and drawing it back down. The stars told us about the galaxy's ancient past. The gas is telling us about its living present and its future, about a galaxy that is still growing, still feeding, still forming stars, still very much alive. And notice how thoroughly this overturns the simple picture we began with. When you look up and see the Milky Way as a bright band across the sky, you're seeing the disk edge on, a thin, bright line of starlight. It looks flat. It looks finite. It looks like the whole of the thing, but everything we've uncovered in these heights above and below tells a different story. The satellites orbit far out of the plane. The stream arcs a third of the way around the sky. The fountain reaches thousands of light years up and down. The high-velocity clouds hang in a halo on every side. The galaxy is not a flat, bright band at all. It is a three-dimensional structure with an enormous, active, gaseous environment above and below the disk, most of which never shines in visible light and so remains completely hidden to the naked eye. But we're not finished. Not remotely. Because so far, even the gas we've discussed, the stream, the clouds, the fountain, is the relatively dense, relatively cool gas that radio telescopes can trace through its hydrogen whisper. There is far more gas out there than this, surrounding the entire galaxy, reaching perhaps 10 times farther than the disk of stars. There is an immense reservoir of gas so hot and so thin that it is nearly invisible even to radio telescopes. A colossal, tenuous ocean that may contain as much ordinary matter as all the stars of the Milky Way combined. It is called the circumgalactic medium, and it dwarfs everything we have yet described. And beyond even that, hanging directly above and below the galaxy's very center, there are two structures so vast and so strange that when astronomers first recognized them, they could scarcely believe what they were seeing. Enormous lobes of high-energy gas towering out of the core. The possible fingerprints of a past eruption from the monster at the heart of the Milky Way. That immense, nearly invisible ocean, and the colossal twin eruptions rising from the galactic center, are where we turn next. Everything we've explored so far. The layered stars, the ancient clusters, the torn ribbons of gas, the falling clouds, the great fountain, all of it still leaves out the single largest component of the galaxy that is made of ordinary matter. And here lies one of the strangest facts in all of astronomy. The thing that may contain more normal matter than every star in the Milky Way put together is something almost nobody has ever heard of, because you cannot see it. Not with your eyes, not with an ordinary telescope, not even easily with the radio telescopes that reveal the streams and the fountains. To find it, astronomers had to invent entirely new ways of looking. And when they did, they discovered that our galaxy is wrapped in an ocean. Let me build up to it carefully because the scale of this thing is hard to grasp. We've been climbing out of the plane and we've watched the stars and the cold gas thin away with height. But the gas never truly stopped. It just kept getting hotter and thinner the higher we went, until it passed beyond the reach of the instruments we've been using. What lies out there, filling the enormous rounded volume that surrounds the entire galaxy, above the disk, below the disk, and stretching out in every direction far beyond the edge of the stars, is a vast halo of extraordinarily hot, extraordinarily diffuse gas. Astronomers call it the circumgalactic medium, which simply means the medium around the galaxy. And it is colossal. How colossal? The bright disk of stars, remember, spans about 100,000 light years. The circumgalactic medium may extend outward for hundreds of thousands of light years in every direction, plausibly reaching several times the diameter of the stellar disk, quite possibly 10 times farther out than the stars you can see. If the visible galaxy is a city, the circumgalactic medium is the vast atmosphere enveloping not just the city, but a whole region hundreds of times larger. An immense, near-invisible ocean of gas in which the bright disk of stars floats like a single glowing island near the center. And here is the truly staggering part. Despite being so thin that it would count as a near-perfect vacuum by any earthly standard, this gas fills such an enormous volume that its total mass is immense. The best estimates suggest the circumgalactic medium may contain as much ordinary matter as much of the everyday stuff that stars and planets and people are made of, as all the stars of the Milky Way combined, possibly even more. Let that settle for a moment. All the hundreds of billions of stars in the galaxy, all their combined mass, may be matched or exceeded by an invisible ocean of gas surrounding them that almost no one has ever heard of. The shining part of the galaxy, the part we've always thought of as the galaxy, may be only about half of the ordinary matter, or less. The rest has been hiding above and below and all around the disk, spread so thin and so hot that it slipped through our vision entirely for most of the history of astronomy. This discovery did more than add a new item to the inventory of the galaxy. It helped resolve a genuine embarrassment that had nagged at astronomers for years. Something they called the missing matter problem. Here's the puzzle. From studying the early universe, cosmologists can calculate quite confidently how much ordinary matter, the everyday kind that makes stars, planets, and gas, ought to exist in a galaxy like the Milky Way. But when astronomers actually added up all the ordinary matter they could see, all the stars, all the cold gas, all the dust, they came up short. Substantially short. A large fraction of the ordinary matter that theory said should be present in and around our galaxy simply could not be found. It was as though you knew from the receipts exactly how much had been spent furnishing a house, walked inside and discovered half the furniture missing. Where had it gone? For a long time, no one could say. The matter was not in the stars, not in the cold clouds, not anywhere the familiar instruments looked. And this is exactly the gap the circumgalactic medium fills. That vast, hot, tenuous ocean surrounding the galaxy, invisible to ordinary telescopes and detectable only by the fingerprints it leaves on distant light and by its faint X-ray glow, turns out to hold a great deal of the ordinary matter that it seemed to be missing. It was never gone. It was hiding above and below and all around the disk, too hot and too thin to shine, waiting for the ultraviolet and X-ray techniques that could finally reveal it. Much of the galaxy's ordinary matter, in other words, was never in the bright part of the galaxy at all. It has always been out in the enormous hidden envelope, And only when we learned to see that envelope did the galaxy's books finally begin to balance. The bright disk we call the Milky Way turns out to contain only a minority of even the ordinary matter that belongs to our galaxy. The majority was in the ocean all along, which raises the obvious question: if it's so massive, why is it so hard to see? Why doesn't this enormous reservoir of gas glow in the sky like the Magellanic Stream does? The answer lies in its temperature and its thinness working together. The cold hydrogen of the stream and the high-velocity clouds glows in the radio at that 21 centimeter whisper precisely because it is cold and neutral, its atoms intact. But the gas of the circumgalactic medium is not cold, and it is not neutral. It is searingly hot, heated to hundreds of thousands or even millions of degrees. At those temperatures, hydrogen atoms don't stay intact. They are torn apart, their electrons stripped away, leaving bare charged particles. Gas in this state is said to be ionized, and ionized hydrogen does not emit that cozy 21 centimeter radio whisper, because it no longer has its electron arranged in the way that produces that signal. So the very technique that let us map the cold streams is nearly blind to this hot halo. And on top of being hot, it is fantastically thin, far thinner than the cold clouds. Thin enough that it emits very little light of any kind. A hot, thin gas is a faint gas. So the circumgalactic medium manages to be simultaneously enormous in mass and nearly invisible, a combination that kept it hidden until astronomers developed the means to detect it by other, cleverer means. How, then, do we know it's there at all? The main trick is beautiful in its indirectness. Instead of trying to see the gas glowing on its own, astronomers watch for the shadow it casts, or rather the fingerprints it leaves, on the light of objects far behind it. Scattered across the distant universe are quasars, the blazingly bright cores of remote galaxies, so luminous they can be seen across billions of light years. When the light from one of these distant beacons passes through the circumgalactic medium, surrounding our galaxy on its way to us, the gas absorbs light at very particular, precise wavelengths, characteristic of the specific ions it contains. So when astronomers spread that quasar's light out into a spectrum, they find dark absorption lines etched into it, gaps at exactly the wavelengths where the intervening hot gas drank up the light. Each of those lines is a signature, a fingerprint, revealing the presence, the temperature, the chemistry, and the motion of the invisible gas the light passed through. By collecting many such sight lines, through the light of many background quasars in many directions, astronomers have painstakingly built up a portrait of a gas halo they can barely see directly at all. Much of this detective work depends on ultraviolet light, a form of light more energetic than the violet our eyes can see, because the ions in this gas leave many of their clearest fingerprints in the ultraviolet. And ultraviolet light from space is blocked by Earth's atmosphere, which means this entire field of study only became possible once we could put telescopes above the atmosphere, in orbit. The discovery of the circumgalactic medium is, in large part, a gift of the space age. A whole invisible half of our galaxy revealed only once we could lift our instruments off the ground and read the fingerprints written in ultraviolet light. The hottest parts of the halo betray themselves in another way too, in X-rays, an even more energetic form of light. Gas heated to millions of degrees glows faintly in X-rays, and X-ray telescopes in orbit have been able to detect this diffuse, super hot emission enveloping the galaxy. In recent years, an X-ray survey of the whole sky revealed the hot gas around the Milky Way on a grander scale than ever before, confirming that our galaxy sits within a vast, roughly spherical envelope of million-degree gas. Between the ultraviolet fingerprints and the X-ray glow, the picture has become undeniable. The Milky Way is cocooned in an immense, hot, tenuous atmosphere reaching out perhaps 10 times farther than its stars, holding a mass of ordinary matter that rivals all those stars combined. And this ocean is not a mere passive container. It is intimately bound up with everything we discussed before. The galactic fountain vents its hot gas up into it. The high-velocity clouds fall down through it. Fresh gas from the wider universe arrives by settling into it first. The circumgalactic medium is the great reservoir, the vast atmospheric sea, within which all their traffic takes place, the medium through which gas must pass on its way into or out of the galaxy. It is, in a real sense, the galaxy's fuel tank and its exhaust cloud at once, the enormous hidden envelope that regulates how much material the disk can gather to build new stars. When we ask what exists above and below the Milky Way, the largest single answer by mass of ordinary matter is this: a nearly invisible ocean of million-degree gas, hundreds of thousands of light years across, that we can only read by the fingerprints it leaves on the light of distant quasars. Now, having filled the space above and below the galaxy with this vast, quiet ocean, I want to take you to the most violent and dramatic structures in the entire halo, because they hang directly above and below the one place in the galaxy where the greatest concentration of power resides: the center, at the very heart of the Milky Way, tens of thousands of light years from us, in the direction of that swarm of globular clusters that first revealed the center's location, sits a supermassive black hole. We call it Sagittarius I star, after the region of sky it occupies. It is a genuine monster by everyday standards, containing about 4 million times the mass of the Sun, all compressed into a region smaller than the orbits of the inner planets. And yet, by the standards of black holes at the centers of galaxies, it is remarkably quiet today. It is not, at present, ferociously devouring great quantities of matter. It sits relatively calm at the galactic core, sipping only occasionally at the gas and stars around it. But it may not always have been so quiet, and that possibility connects directly to a discovery that astonished astronomers when it was announced. A discovery of two structures so enormous and so unexpected that they went entirely unnoticed, looming above and below the galactic center, until the right kind of telescope finally revealed them. The story of that discovery begins with gamma rays, the most energetic form of light in the universe, far beyond ultraviolet, far beyond X-rays. Gamma rays are produced only in the most violent, high-energy processes, and like ultraviolet and X-rays, they are blocked by Earth's atmosphere. So to detect them, we must go to space. A gamma-ray telescope in orbit spent years scanning the whole sky, mapping where these ferociously energetic photons were coming from. And when astronomers carefully subtracted away all the known sources of gamma rays and looked at what remained, they found something that took their breath away. Rising out of the galactic center, above the plane and below the plane, were two colossal lobes of gamma ray emission. Two vast rounded bubbles of high energy gas, one towering upward out of the disk, and one plunging downward, arranged symmetrically about the center like a titanic figure eight, or like two enormous balloons inflated from the galactic core, one above and one below. Astronomers named them the Fermi bubbles, after the telescope that found them, and their size is almost impossible to overstate. Each bubble reaches something like 25,000 light years out from the plane. Taken together, top to bottom, the two bubbles span something like 50,000 light years, which is comparable to a substantial fraction of the entire diameter of the galaxy's visible disk. These are not minor features. They are among the largest structures associated with the Milky Way. Two gigantic lobes of energetic gas erupting from the center, filling the space above and below the core on a scale that rivals the whole bright galaxy itself. And once astronomers knew to look for them, they found echoes of the bubbles in other forms of light too. There are corresponding structures visible in X-rays and features in radio waves, all lining up with the gamma ray lobes, all pointing to the same conclusion. Something poured an immense amount of energy out of the galactic center, above and below the plane, carving these enormous cavities of hot, energetic gas into the halo. The recent X-ray sky survey I mentioned earlier revealed even larger related features, vast X-ray lobes enveloping the gamma ray bubbles, suggesting the affected region may be grander still. So, what created them? What could possibly inflate two lobes of energetic gas 50,000 light years tall, one above and one below the galactic center? This is where I have to be very honest with you, because the exact origin of the Fermi bubbles is not settled. It remains a genuinely open question, actively investigated and debated. What astronomers have are strong, plausible leading ideas, not a final answer. And it's worth understanding those ideas, precisely because they show how the space above and below the galaxy records the violent history of its center. The first leading idea points the finger at Sagittarius I star itself, the supermassive black hole at the core. Black holes at the centers of galaxies, when they are actively feeding, are among the most powerful engines in the universe. As matter spirals in towards such a black hole, it heats up, compresses, and can launch tremendous outflows. Jets and winds of energetic material blasted outward at enormous speeds, carrying staggering amounts of energy far out of the galactic center. Today, our black hole is quiet, but the Fermi bubbles may be the fading monument to a time when it was not, a period, perhaps a few million years ago, when Sagittarius E star fed voraciously on gas falling into the core, and, in doing so, blasted two great outflows of energetic material up out of the plane and down below it, inflating the bubbles we now see. Under this picture, the bubbles are essentially fossilized evidence of a past outburst of the central black hole. A record written across 50,000 light years of sky, of an era when the sleeping monster at our galaxy's heart was violently awake. The second leading idea places the blame not on the black hole itself, but on a tremendous burst of star formation near the galactic center. The central regions of the galaxy contain dense concentrations of gas, and if a great many stars formed there in a relatively short span, the most massive of them would have died in a rapid succession of supernova explosions, a concentrated storm of stellar detonations at the core. The combined energy of countless supernovae erupting close together could, like a scaled-up version of the galactic fountain we met earlier, drive enormous outflows of hot gas up out of the plane and down below it, inflating the bubbles. Under this picture, the Fermi bubbles are the grandest expression of the fountain phenomenon, powered not by the black hole, but by a burst of stellar birth and death at the galactic center. It is entirely possible, too, that the truth involves some combination, or that both the black hole and central star formation have contributed at different times. Astronomers continue to study the bubble's precise shape, their edges, their energy content, and the age implied by how far they've expanded, trying to distinguish between these scenarios. Estimates for how long ago the defining event occurred generally point to a few million years, astonishingly recent in cosmic terms, which is part of why the discovery is so striking. Whatever inflated these titanic lobes did so not in the distant youth of the galaxy, but relatively recently, well after complex life had already arisen on Earth. But the essential, honest point is this: we see the bubbles clearly. We know they represent an enormous injection of energy above and below the galactic center. And we have compelling ideas about their origin. But we do not yet know for certain which is correct. The space above and below the galaxy holds, in these two vast lobes, a dramatic unsolved mystery. A puzzle whose solution will teach us about the violent history of our own galaxy's heart. The Fermi bubbles also connect to two more ingredients of the halo that reach far above and below the disk, and that we should bring into the picture: cosmic rays and magnetic fields. Cosmic rays are not rays of light at all, but individual particles, atomic nuclei and electrons, accelerated to nearly the speed of light by violent events like supernova explosions and outflows from the galactic center. These ferociously energetic particles stream outward through the galaxy and far up into the halo, and they are, in fact, part of what makes the Fermi bubbles glow in gamma rays, as high-energy particles within the bubbles interact with gas and light to produce the energetic radiation. Cosmic rays pervade the space above and below the disk, a population of relativistic particles filling the halo, launched from the disk and the center, and spiraling out into the heights. And they do not travel in straight lines, because the galaxy is threaded with magnetic fields. The Milky Way possesses a large-scale magnetic field, generated by the churning motions of gas and the galaxy's rotation. And this field does not stay politely confined to the disk. It reaches up out of the plane, threading the halo above and below, its invisible lines of force guiding the motions of charged particles and helping to shape structures like the bubbles. Cosmic rays spiral along these magnetic field lines, and the pressure of the cosmic rays and magnetic fields together helps push gas up out of the disk, contributing to the fountain and to the great outflows. So the space above and below the galaxy is not just filled with gas and stars and the ghosts of shredded companions. It is also filled with invisible magnetism and with a rain of near light speed particles, an energetic, magnetized environment extending far beyond the visible disk. Let's gather all of this together, because step by step, the picture of what lies above and below the Milky Way has grown almost unrecognizably richer than the simple bright band we started with. We found layers of stars, the thin disk, the thick disk, and the vast ancient stellar halo, studded with globular clusters. We found a second galaxy made of gas, the Magellanic stream, and its companions, the tilted swarm of satellite galaxies, the falling high-velocity clouds, and the ceaseless breathing of the galactic fountain. And now we have found two more things grander still. First, the circumgalactic medium, an immense, nearly invisible ocean of million-degree gas, reaching perhaps 10 times farther than the stars, and containing as much ordinary matter as all of them combined. Detectable only by the fingerprints it leaves on the light of distant quasars, and by its faint X-ray glow. And second, the Fermi bubbles, two colossal lobes of energetic gas towering 50,000 light-years above and below the galactic center, threaded with cosmic rays and magnetic fields, most likely the monument to a violent outburst, from the central black hole, from a storm of supernovae, or from both, whose exact origin we are still working to pin down. Notice how completely this reframes the galaxy. The bright disk of stars, the thing we call the Milky Way when we look up at night, turns out to be almost the least of it, by volume and even by mass of ordinary matter. Surrounding that disk, above it and below it, is a structure vastly larger, mostly invisible, mostly hot or mostly dark, that we have only learned to perceive by reaching beyond visible light into the radio, the ultraviolet, the X-ray, and the gamma ray, and by lifting our instruments above the atmosphere into space. If you could see all the wavelengths at once, the Milky Way would not look like a thin, bright band at all. It would look like an enormous glowing sphere of hot gas, with two great energetic lobes erupting from its heart, and a thin, bright disk of stars buried at its center, like a filament inside a vast, luminous bulb. And yet, for all this immensity, we still have not accounted for the largest component of the galaxy at all. Because everything I've described tonight, every star, every cloud, every stream, the entire vast circumgalactic ocean, all of it put together, all the ordinary matter, is still only a fraction of the true mass of the Milky Way. The overwhelming majority of the galaxy's mass is something else entirely. Something that emits no light of any wavelength, that casts no fingerprints on quasar spectra, that we cannot photograph even in principle. It is inferred only by the pull of its gravity, and it dwarfs everything else. It surrounds the galaxy in a halo larger than the stellar halo, larger even than the circumgalactic medium, the true outermost envelope of the Milky Way, and it forces upon us at last the deepest question of the night. Where, if anywhere, does the galaxy actually end? That final invisible scaffolding, the shredded fossil streams that trace it, and the question of the galaxy's true edge are where we go now. We have filled the space above and below the Milky Way with an astonishing amount of material. Layers of stars, ancient clusters, torn ribbons of gas, falling clouds, a breathing fountain, an invisible ocean of million-degree gas, two colossal lobes of energetic gas erupting from the core. And after all of that, here is the fact that puts everything else in its place. Every single thing we have discussed tonight, every star, every atom of gas, every particle in every stream and bubble and cloud, all of it added together, amounts to only a small fraction of the total mass of the galaxy. Roughly speaking, all the ordinary matter, all the stuff that shines or glows or can be traced by any form of light at all, makes up something like a sixth of the Milky Way's mass, or even less. The other 5/6, the overwhelming majority of the galaxy, is something we cannot see by any means whatsoever. We call it dark matter, and it is the true dominant substance of the galaxy above and below the plane. I want to be very precise about what dark matter is and is not, because it is easy to mystify, and it does not need mystifying. Dark matter is not a metaphor, and it is not a placeholder for our ignorance in some vague sense. It is a specific, concrete inference drawn from the behavior of things we can see, and the reasoning is remarkably solid. Here is the core of it. When you watch how stars and gas move within the galaxy, their motion is governed by gravity, and gravity is governed by mass. The faster things orbit, the more mass must be pulling on them. So by measuring how fast stars and gas circle the galaxy at various distances from the center, astronomers can weigh the galaxy, can calculate how much mass must be present to produce the motions they observe. And when they do this, they find something that cannot be explained by the visible matter alone. Out in the far reaches of the galaxy, stars and gas clouds orbit far too fast. They move as though there's a great deal more mass pulling on them than all the stars and gas could possibly account for. If the visible matter were all there was, these outer objects should orbit slowly, the way distant planets orbit the sun more slowly than near ones. Instead, they orbit swiftly, as though gripped by the gravity of some enormous unseen mass spread throughout and around the galaxy. That unseen mass is dark matter. It is called dark not because it is black or shadowy, but because it does not interact with light at all. It emits no light, absorbs no light, reflects no light. It is transparent to every form of radiation we've discussed. Radio, infrared, visible, ultraviolet, X-ray, gamma ray, all of it passes straight through as though the dark matter weren't there. And yet, it has mass. And so it has gravity. And it is that gravity, and only that gravity, that reveals it. We know it is there in the same way you would know an invisible person was in a swimming pool by watching the water swirl, or the way you might sense a heavy object under a stretched sheet by the way the sheet sags. We see the sag. We measure the swirl. We infer the mass. We cannot see the thing itself. And when astronomers map out where all this inferred mass must be, they find that it forms an enormous, roughly spherical halo enveloping the entire galaxy, above the disk, below the disk, and in every direction, far larger than the stellar halo, far larger even than the vast circumgalactic ocean of gas. This is the dark matter halo, and it is the true outermost bulk of the Milky Way. Its exact size is uncertain, precisely because you cannot see an edge on something invisible, but it plausibly reaches out several 100,000 light years in every direction, dwarfing the 100,000 light year disk of stars many times over. The bright disk we see is a small, dense knot of luminous matter sitting near the center of a titanic, invisible sphere of dark matter that outweighs it many times and outreaches it many times. Now, it is crucial to keep three different halos distinct in your mind, because they are easy to blur together and they are genuinely different things. First, there is the stellar halo, made of real, actual stars, ancient and metal poor, sparse but shining, the swarm of old stars and globular clusters we explored earlier. Second, there is the gaseous halo, the circumgalactic medium, that immense ocean of hot, thin, ionized gas reaching perhaps 10 times farther than the stars. And third, larger and more massive than both combined, there is the dark matter halo, made of that invisible substance we can only infer through gravity. All three are roughly spherical. All three surround the disk above and below, but they are made of different things and detected in completely different ways. The stellar halo shines faintly in visible light. The gaseous halo betrays itself in ultraviolet and X-ray fingerprints. The dark matter halo reveals itself only through the gravitational pull it exerts on everything else. Blurring them together loses the whole richness of the picture. Above and below the Milky Way, there are three great nested spheres. Three different halos, one of stars, one of gas, and one of darkness. What is the dark matter actually made of? This is one of the great unsolved questions in all of science, and I won't pretend we have the answer, because we don't. It is not ordinary matter in some hidden form. careful reasoning has ruled out the possibility that it's simply faint stars or cold gas or rogue planets or ordinary black holes in the numbers required. It appears to be some entirely new kind of matter, some type of particle that has mass and gravity but does not interact with light or with ordinary matter in the ways familiar particles do. Enormous experiments have been built deep underground to try to catch even a single one of these particles directly, and so far, none has been unambiguously caught. We know dark matter is there with tremendous confidence, from many independent lines of evidence, in the galaxy, in other galaxies, in the way galaxies cluster, in the structure of the whole universe, but what it fundamentally is remains genuinely unknown. It is a colossal, invisible presence, filling the space above and below our galaxy, whose very identity is still a mystery. So the dark matter halo is the invisible scaffolding, the dominant mass, the true bulk of the galaxy. But here is a beautiful thing. Even though we cannot see the dark matter, we can, in a sense, trace its shape and probe its structure using the visible things that move within it. And the most exquisite traces of all are objects called stellar streams. To understand them, we return one last time to the theme that has run through this entire night. That the Milky Way grows by devouring its smaller companions. We saw earlier that satellite galaxies orbit the Milky Way on tilted paths, high above and far below the plane. We saw the tidal forces tear gas out of them, as with the Magellanic stream. But tidal forces do not only strip gas. Given enough time and a close enough passage, they can tear an entire small galaxy or globular cluster completely apart, pulling its stars out one by one and stringing them along the object's orbit. Picture a small dwarf galaxy or a globular cluster falling in towards the Milky Way, plunging along one of those great looping halo orbits. As it swings close to the galaxy, the Milky Way's tidal forces pull harder on its near side than its far side, and stars begin to leak away. Some pulled slightly ahead along the orbit, some falling slightly behind. Over many orbits, over hundreds of millions or billions of years, more and more stars are stripped until the little galaxy is drawn out into an enormous, thin, arcing ribbon of stars following the path of its orbit, wrapping part way or even multiple times around the Milky Way, high above and far below the plane. These ribbons of stripped stars are the stellar streams, and they are precious beyond words for two reasons. The first reason is that they are fossils. A stellar stream is the visible, unwinding corpse of a galaxy or cluster that the Milky Way is in the process of eating. Each stream marks the ongoing destruction of one of our galaxy's companions. Its stars spread out along the orbit like a trail of breadcrumbs, marking where the victim traveled. By studying the streams, we can identify individual objects being consumed right now and read directly the process by which the Milky Way grows. The most spectacular example is the Sagittarius stream, the shredded remains of a dwarf galaxy that has been torn apart and stretched into a vast arc of stars, looping all the way around the Milky Way, high over the poles of the disk, above and below the plane. That dwarf galaxy is being devoured before our eyes, its stars strewn across the halo in a titanic ring, a single galaxy's worth of stars unspooled across the sky. It is the clearest possible demonstration that the Milky Way is not a finished, static object, but a still hungry galaxy, actively cannibalizing its neighbors, and that the space above and below the disk is where the evidence of that feeding is written. The second reason stellar streams are precious is subtler and even more powerful. Because a stream is a line of stars following a single orbit through the halo, and because that orbit is shaped by gravity, the exact path of the stream is exquisitely sensitive to the distribution of mass it moves through, including the invisible dark matter. If the dark matter halo were perfectly smooth, the streams would trace smooth, clean arcs. But if there are lumps and clumps of dark matter scattered through the halo, as many theories predict there should be, then a stream passing near such a clump would be gravitationally tugged, gaining a kink, a gap, a subtle disturbance in its otherwise smooth arc. So by studying the fine structure of stellar streams, by looking for gaps and wiggles and disturbances, astronomers can effectively map the invisible dark matter of the halo, using the visible stars of the stream as a probe. The streams are like threads laid across the invisible landscape of dark matter, and every kink in a thread reveals an unseen hill or valley beneath it. In this way, the shredded remains of devoured galaxies, strung out above and below the plane, become one of our finest tools for charting the very dark matter that dominates the galaxy's mass. This technique matters for a reason that reaches beyond simply weighing the galaxy. One of the sharpest tests of what dark matter actually is comes down to a single question. Is it smooth, or is it lumpy? Different ideas about the nature of the dark matter particle make different predictions here. Some predict that the great halo above and below the disk should be studded with countless small, dense clumps of dark matter, thousands of them, most containing no stars at all, and therefore utterly invisible by any direct means. Other ideas predict a far smoother halo, with the small clumps smeared out or never formed. There is, at first glance, no way to tell these apart because the clumps, if they exist, emit nothing and reflect nothing. But a stellar stream changes that. A long, thin ribbon of stars threading the halo is the perfect tripwire. If one of these dark, starless clumps drift through a stream, or the stream sweeps past one, the clump's gravity plucks at the passing stars and tears a small gap or a subtle kink in the otherwise smooth ribbon, a scar left by an encounter with something wholly invisible. So astronomers now comb the known streams, looking for exactly these gaps and disturbances, using them to count, in effect, the invisible clumps the streams have brushed against. Finding the gaps would confirm that the halo above and below the plane is riddled with dark, starless lumps, and would rule out whole classes of theories about what dark matter is. It is a remarkable situation. The fossilized corpses of shredded dwarf galaxies strung across the heights above the disk are being used to hunt for the invisible debris of an entirely unseen kind of matter. To find and study these streams and the wider population of halo stars, astronomers needed to do something that sounds almost impossibly ambitious: to measure the positions, distances, and motions of vast numbers of individual stars across the whole galaxy, precisely enough to pick out the faint, coherent streams from the general scatter of halo stars. And in recent years, one mission above all transformed this from a dream into a reality. A space observatory called Gaia was launched with a single overriding purpose: to map the galaxy in 3 dimensions with unprecedented precision, charting the positions and motions of well over 1 billion stars. More than 1 billion stars, each one measured, its position on the sky pinned down, its distance estimated, its motion across the sky tracked, and in many cases, its velocity toward or away from us measured too. It is, without exaggeration, the most detailed map of the Milky Way ever made, a genuine three-dimensional survey of 1 billion suns. And what Gaia revealed when astronomers began to sift through its titanic catalogue was breathtaking, and it speaks directly to everything we've explored above and below the plane. Because when you can measure not just where stars are, but how they are moving, you can find groups of stars that share a common motion. Stars that are all traveling together through the halo in the same direction at the same speed, even if they are now spread across a wide swath of sky. And stars that move together very often were born together, or fell in together, as part of some now dissolved structure. Gaia let astronomers do galactic archaeology on an industrial scale, sorting the halo stars by their motions and uncovering the debris of ancient events long since scattered across the sky. The streams lit up in the Gaia data, their member stars picked out by their shared, coherent motion along common orbits above and below the plane. But Gaia revealed something even more profound than the streams that were still recognizable as streams. It revealed the debris of collisions so ancient that the victim galaxies had been completely dissolved, their stars fully mixed into the halo, no longer forming a visible ribbon at all, and yet still betraying their common origin through their shared motions. The most dramatic discovery was the evidence of an enormous ancient collision. Billions of years ago, in the youth of the Milky Way, a substantial galaxy fell into ours and was completely torn apart and absorbed, its stars flung onto a distinctive set of orbits that Gaia could still detect billions of years later. A whole population of halo stars all moving in a characteristic way that marked them as the shredded remains of that long-dead intruder. Astronomers gave this vanished galaxy a name, calling the event the merger with a galaxy sometimes referred to as Gaia Enceladus, or from the distinctive shape its debris traces when plotted by motion, the Gaia sausage. It was one of the most important events in our galaxy's history, a major collision that helped build the very stellar halo we've been exploring, and its fingerprints lay hidden in the motions of halo stars until a space telescope precise enough to detect them was finally built. And Gaia has not worked alone. Its precise map of stellar motions is at its most powerful when combined with other surveys that measure the detailed chemistry of those same stars, splitting their light apart to read the exact mix of elements each one contains. Remember that a star's chemistry is a kind of birth certificate, the point we drew out much earlier. Stars that form together in the same long-dead galaxy tend to share a distinctive chemical fingerprint, one that differs subtly from stars born in the Milky Way itself. So astronomers now cross-reference the two kinds of data, motion from Gaia and chemistry from these spectroscopic surveys, and the combination is like having both the fingerprints and the movements of everyone at a crime scene. Groups of halo stars that share both a common motion and a common, unusual chemistry can be confidently identified as the shredded remains of a single, vanished galaxy, even when their stars are now scattered clear across the sky above and below the plane. This double approach has begun to reveal something striking about the structure of the stellar halo itself. It appears to be built in layers, an inner region and an outer region with different origins. The inner stellar halo, closer to the disk, seems to contain a large contribution from that one great ancient collision, the debris of the major galaxy the Milky Way swallowed in its youth, its stars now settled into the inner heights. The outer stellar halo, reaching much farther above and below the plane, seems to be a more chaotic patchwork. Assembled from many smaller, later, and more varied victims, dwarf galaxies captured and dismantled at different times and from different directions. In other words, the halo is not a single uniform cloud, but a stratified record, with the largest, oldest meal laid down closer in, and a scattering of smaller, more recent meals spread out beyond it. Reading those layers, sorting which halo star came from which devoured companion, is one of the most active frontiers in mapping our galaxy's past, and it is only possible because we can now measure both how the stars above and below the disk are moving and what they are made of, for millions of them at once. Step back then, and feel the full weight of what these motions and chemistries are telling us. That sparse cloud of ancient metal-poor stars we met at the very beginning of the night, hanging high above and far below the plane, is not simply the galaxy's own firstborn stars quietly aging in place. A great deal of it is wreckage, layered and sorted, the largest ancient victim laid down within, and a scattering of smaller ones strewn beyond. The halo is a graveyard and a battlefield record all at once, and only now do we possess the means to read it. So when we look at the stars above and below the disk, we are very often gazing at the remains of other galaxies, the digested meals of our own, and the Milky Way, in a real and literal sense, has been assembled partly out of the neighbours it consumed, a history written plainly across the heights and depths on either side of the plane. So now we have assembled the complete picture, and it is time to confront the question that has been waiting for us since the very first words of tonight. If the Milky Way is all of this, the bright thin disk, the thicker disk, the sparse stellar halo full of shredded companions, the immense gaseous ocean, the two great energetic lobes, and the dominant invisible dark matter halo reaching hundreds of thousands of light years in every direction, then where exactly does the galaxy end? Where's its edge? Where is the boundary beyond which you have left the Milky Way behind? And the honest, careful, scientifically accurate answer is this: there is no single edge. The question does not have one answer, because the answer depends entirely on what you mean by the galaxy. And that is not a dodge or an evasion. It is one of the deepest truths about the nature of our galaxy. And understanding why is the real payoff of the whole night. If by the galaxy you mean the bright disk of stars, the thing you see as a band across the sky, then the edge is relatively near, out at perhaps 50,000 light years from the center, where the disk of stars fades away. But we have seen that this is only the innermost, brightest slice. If by the galaxy you mean the stellar halo, the full extent of stars, including the sparse, ancient ones, and the shredded streams, then the edge is much farther out, reaching well over 100,000 light years from the center, and it fades so gradually that pinning a single number to it is somewhat arbitrary. The stars simply grow sparser and sparser, with no clean boundary. If by the galaxy you mean the gaseous halo, the circumgalactic medium, then the edge is farther still. That ocean of hot thin gas reaching perhaps 10 times the radius of the stellar disk, hundreds of thousands of light years out, again with no sharp boundary but a gradual thinning into the space between galaxies. If by the galaxy you mean the reach of its gravitational influence, the region within which the Milky Way's gravity dominates over that of its neighbors, then you are talking about a boundary shaped by the tug-of-war between our galaxy and others, particularly the great Andromeda galaxy, and it lies somewhere in the vast gulf between the two. And if by the galaxy you mean the dark matter halo, the true dominant mass of the whole system, then the edge is the farthest of all, reaching out several 100,000 light years, an enormous invisible sphere whose outer boundary is genuinely fuzzy, because dark matter simply grows more and more diffuse until it blends imperceptibly into the general dark matter of the wider universe. So the Milky Way does not end at one sharp physical edge, the way a coin or a planet ends at a clean surface. It has no crisp rim. Instead, it has a whole series of nested, gradually fading boundaries, each corresponding to a different component, each at a different distance, none of them sharp. Where the galaxy ends depends on whether you ask about the stars you can see, the stars you can barely see, the gas you can detect only by its fingerprints, the gravity you can measure, or the darkness you can only infer. The galaxy fades outward through layer after layer, each one dimmer and more diffuse than the last, until at some ill-defined distance you must simply admit that you are now more in the space between galaxies than within our own. The Milky Way, in the end, does not stop. It trails off. Let me try to give you one intuitive image to hold all of this together, a way to feel the true proportions of the thing. Imagine the bright disk of stars, the Milky Way you see at night, shrunk down to the size of a large dinner plate lying flat on a table. At that scale, as we said at the very start, the bright disk of stars is thinner than a sheet of cardboard, and it spans the width of the plate. Now, the stellar halo, the sparse ancient stars and streams, would form a faint spherical haze, extending a little beyond the edge of the plate in all directions. Above and below the table's surface, a dim glow surrounding the bright plate. The circumgalactic medium, the gaseous ocean, would fill a vast invisible sphere many times wider than the plate, reaching most of the way across the whole table. And the dark matter halo, the true bulk of the galaxy, would be a titanic invisible ball, larger still, engulfing the entire table and reaching well beyond its edges, with the bright glowing plate sitting tiny and luminous at its very center. That is the honest shape of our galaxy, a small, brilliant, wafer-thin disk of light, buried at the heart of an enormous, mostly invisible, roughly spherical structure hundreds of times larger, made of sparse stars, thin, hot gas, and above all, dark matter. And this is precisely why I asked you at the very beginning to imagine the bright disk of the Milky Way simply switching off. Because if it did, if every star you could see vanished in an instant, the galaxy would not vanish with them. Almost all of it would remain. The vast dark matter halo, unchanged, would still be there, hundreds of thousands of light years across, holding the whole system in its gravitational grip. The immense ocean of hot gas would still be there, glowing faintly in ultraviolet and X-ray. The sparse stellar halo, the shredded streams, the globular clusters riding high above and below the plane, the two great energetic lobes towering from the core, the ribbons of gas torn from our companions, the falling clouds, the breathing fountain, all of it would still be there, hanging in the space above and below where the bright disk used to be. The luminous spiral we called the Milky Way, the thing that named our galaxy, the thing humans have gazed at and told stories about for all of history, turns out to be only the thin, bright, innermost skin of something incomparably larger, older, stranger, and mostly invisible. That is the revelation the space above and below the galaxy has been holding for us all along. When you look up on a dark night and see that soft band of light arching overhead, you are not seeing the galaxy. You're seeing a slice of it, a single bright layer, edge on, buried deep inside a structure so much greater that the visible band is almost a rounding error in the total. Above that band and below it, mostly hidden from your eyes, stretches the true Milky Way, layered and nested, feeding and breathing, cannibalizing its neighbors and cradling their remains, wrapped in an ocean of unseen gas, crowned with the fossil of an ancient eruption, and held together, above all, by an invisible darkness we can weigh but cannot see and do not yet understand. The galaxy does not end where the light ends. It reaches on, into the dark, far above and far below the glowing plane, for hundreds of thousands of light years, further than the eye could ever suggest. And knowing that, truly grasping it, you can never look at that quiet band of light in quite the same way again. What you see is real, but what you cannot see is almost everything.